a cargo de Fermín Dravi, del Laboratorio de Inteligencia Artificial Aplicada. Adelante, Fermín.
Hola, sí. No se ve el video, me parece, ¿no?
Sí, se ve
la
la
imagen,
imagen.
sí, pero el video, bueno.
La imagen,
Bueno.
sí, sí.
Bueno, gracias. So I'm going to talk about visual search in natural scenes, models comparison, and reference datasets.
Perdón, Fermín, habrá un poquitito más fuerte,
Okay,
que se escucha. Sí, no tiene buen sonido tu micrófono.
Okay, so visual search in natural scenes consists of looking for a target object in an image that resembles everyday life. But when we look at a scene, we don't see everything in high definition, but rather there's a small portion of the eye, called the fovea, in which we are able to see high definition and the rest is kind of blurry. So when we look for a target, we move our eyes from one place to the other until we find the target. And this produces what we call a scan path, which is an ordered list of fixations. So we have as input a search image and a target. These are going to go through 3 different visual search models. And we also have human subjects data on these images. These are the datasets. So we have one scan path per model and one scan path per subject for each image. And then we're going to compare the two to see how similar they are. This is an example scan path, one for each model, and these are those of human subjects. So for the datasets, we have 4 very different datasets. One of them is an unrestricted dataset, which is the only one to contain people or human faces in it. Another one is the interiors dataset, which is the only one to contain distractors, that is, objects that belong to the same category as the target. So human subjects were required to find the exact target in the image. For instance, if a cup was presented, then they had to look for this specific cup in the image, and there could be others. But the other 3 datasets use a generalized version of the target. For instance, if they had to look for a cup, they had to look for any cup in the image, but there was only one of them. In MCS, targets are restricted to microwaves and clocks, and in Coco Search 18, there are 18 different target categories. There could be a car, a bottle, a chair, and so on. Keep in mind that only scan paths where a target was found are taken into account. As for the models, one is AVSN, which is based on a convolutional neural network. It is zero shot, this means it was not trained on visual search data, and it makes an emphasis on capturing object invariance. And it builds an attention map by forwarding both the search image and the target image in the CNN. This is an example of attention map, and you can see that it is brightest in the spot where the target is located. And then a greedy search is performed on this attention map, which means the whole image is processed at once in high definition, contrary to how human vision works. Another model is CIVS, which is a Bayesian model. As prior, it uses a saliency map. This is an example of a saliency map. It captures the most relevant parts of an image. And the likelihood is computed through a visibility map, which is a Gaussian blur applied on the center of fixation, and a target similarity map, which tells us how similar each portion of the image is to the target. And this was computed through cross-correlation, but here we're going to use AVSN's attention map as the target similarity map. So now the model is able to capture object invariance instead of just cropped targets. This means that it can look for any cup in the image instead of a specific cup. This model is called Neural Network IVS or NIVS. Finally, we have REL, which is based on inverse reinforcement learning. It was trained on Coco Search 18. This means it is the only model trained on human data, and it uses a generator-discriminator architecture. It attempts to incorporate context by preprocessing the search image with an object detector. This is an example of the preprocessed image, and you can see that each pixel belongs to a category. For instance, these pixels belong to a couch, these belong to a chair, and these belong to a cabinet. So the model never actually sees the original image, but instead it sees this set of masks. And to model the fovea, it does something very similar to an IVS, where a Gaussian blur is applied centered on the current fixation. As it was trained on Coco Search 18, it can only search on those 18 object categories, so it can only be tested on a small subset of the interiors and unrestricted datasets. As for the metrics, we have 2 different metrics. One is cumulative performance, which measures the ratio of targets found for a given number of fixations. It's a measure of efficiency. And we also measure scan-path similarity using multi-match. We're going to plot the within humans scan-path similarity as a function of humans model scan-path similarity. So this means that the closer these points are to the diagonal, the more similar the model scan-paths were to those of human subjects. Each one of these points corresponds to an image. So it's a quick overview of the results. In blue is human subjects data, and in green is a VCN. You can see it had a great search performance in every dataset, but its scan-paths were dissimilar to those of human subjects, as the points are leaning towards the left. Ariel is in red, and it had a great performance in some dataset, but in the other 3 datasets it achieved below 50% accuracy, so it was pretty poor. And NIVS produced the most similar human scan-paths, in comparison to human scan-paths. And with regard to the efficiency, it was the most similar to human subjects, with the exception of Coco Search 18. So these are some examples where the dissimilarity between human subjects and visual search models was greatest. In this case, the target was a car, and you can see that human subjects immediately fixated on the road when looking for a car. But visual search models look for it even in buildings, because they aren't aware of the fact that cars are usually on roads. Another example is a potted plant in a kitchen. You can see visual search models look for it even in lamps or in the ceiling, but human subjects only look for it at the kitchen counter level. The same goes for a bottle placed in a bathroom. Visual search models again look for it in a bathtub, but human subjects look for it or expected it to be placed on top of something, such as a table, so they look for it here. So to sum up, NIVS produced the most human-like scan-paths. This was done by modeling the visual system within a DNN framework, that is a CNN, while applying a Bayesian approach for the central decision-making. But nevertheless, combining scene content with the target's meaning remained elusive for these state-of-the-art visual search models. This means that context is important, and even though Ariel made a first step in this direction, this approach is not generalizable. And future research should take this factor into account. So all of the code is here, including the search models, plots, metrics, and the preprocessed datasets are available in Python in my GitHub page at Visual Search Benchmark. And these are the references. Thank you for listening.
Muchas gracias, Fermín, por tu presentación. Estamos pasados en tiempo, pero bueno, tenemos tiempo para una pregunta, aunque sea.
Una preguntita.
Sí.
¿Cómo que se puede incorporar el contexto? Es re difícil lo que está pasando.
Sí, uy, se me fue la presentación.
¿Cómo pones esto?
Sí, una de las ideas es hacer algo similar con el modelo bayesiano, cambiarle el prior para que no use un mapa de saliencia, sino hacer algo similar a lo que hizo el modelo IRL, que es usar la ubicación de los objetos. Claro. Entonces lo que puedo hacer es agarrar, por ejemplo, un dataset muy grande, donde están todas las anotaciones de los objetos, y hacer un mapa donde están comúnmente esos objetos. Por ejemplo, dónde están comúnmente los autos, dónde están comúnmente botellas o plantas. Y usar eso como el prior en el modelo bayesiano. Esa es una idea que a futuro se podría explorar.
Bueno, muchas gracias. Como estamos pasados un poquito de tiempo y así